A study found the body temperatures of 106 healthy adults. The sample mean was 98.2 degrees, and the sample standard deviation was 0.62 degrees. Find the margin of error E and the 95% confidence interval mu. Does the interval contradict the claim that the body temperature of healthy adults is 98.6 degrees? All right, so when I read the problem, I can see that it's a 95% confidence interval that we're looking for. It also mentions we're trying to find the margin of error, but that's part of the confidence interval, so we'll get that as part of the process. Let's start by writing down all the information from the problem that's going to be useful for us. So we're going to need an n in the problem, we're going to need an x bar in the problem, we're going to need a standard deviation, and we'll need a confidence level, which will lead us to alpha. All right, so the n is 106 because it says we had 106 healthy adults. The sample mean, it says the sample mean was 98.2. The standard deviation for the sample, it says, was 0.62. And the confidence level is 95%. If the confidence level is 95%, it means that alpha is 0.05. All right, so that's the data for the problem. Our next step is to determine what the z alpha divided by 2 value is. So z alpha divided by 2. Now we choose z because our n is 106. We have a large sample size, so we'll go ahead and use z here. The z alpha divided by 2 value is going to depend upon alpha. So alpha divided by 2 here is going to be z 0.025. So we're going to look in the 0.025 column of the t-table to find that number. So let's go do that now and come back with that value. Okay, so we're looking up the 0.025 in one tail, and we go straight to the bottom because our sample size is large, and let's see what that gives us in the end. So scrolling down, we find that our answer then becomes 1.96. 1.96 is our critical z alpha divided by 2 value. Okay, so that value turns out to be 1.96. Now that we have that value, we're going to go ahead and use it in the margin of error formula. So we're using the formula E is equal to z alpha divided by 2 sigma over the square root of n. Okay, so we have z, it's 1.96. Sigma we don't have directly, but we do have a sample estimate of it, so we're going to use that instead. So we use 0.62 divided by the square root of 106, which is our n, square root of 106. And let's work that out in the calculator and see what that gives us. Okay, so if I use my calculator here, I'll have 1.96 times 0.62 divided by the square root of 106. Okay, I'm going to close that up, hit enter, and see what it gives us then. All right, so the total error turns out to be 0.1180 ... So it goes on and on. I'm just going to use that number stored in my calculator for the next step. Okay, so our next step, and the final step really of the calculation, is to do the sample mean minus the error and the sample mean plus the error. So for us, that's going to work out to be, in this case, 98.2 minus, let's say, 0.118, and then 98.2 plus 0.118. I'll close it up, and let's see what that gives us for the answer. So we're going to have 98.2 minus the error, and then the same thing plus the error. I'm going to go ahead and round that off to the same decimal place that I have for the sample mean. So my final result works out to be this: 98.1 degrees up to 98.3. Okay, so remember, we are 95% confident that the true mean body temperature for healthy adults is between 98.1 degrees and 98.3 degrees Fahrenheit, right? Now, we have a question at the end of the problem here that asks us very simply, does the interval contradict the claim that the body temperature of healthy adults is 98.6 degrees? What we're checking on here is if the mean that we've always heard our whole lives of 98.6 is part of this interval. Because remember, this interval is supposed to contain the population mean. Well, the interval doesn't have 98.6 in it. So that means that this interval does contradict the common belief that 98.6 is the healthy body temperature. Okay, so from there, of course, you have to look at this as this is one study and it contradicts the belief that we've held for a long time, and usually researchers would need to see a little more evidence to be sure that that is in fact correct, that 98.6 is not the proper average body temperature for healthy adults. But at least this one study seems to contradict that belief. Okay, so let's go on then and look at this last part of the problem. I've left here in the notes a part of the notes that goes over some ideas, and I just want to discuss those briefly. So the first thing I want to look at is this idea that as the confidence goes up, so does the interval width. The interval actually gets wider when you have a higher confidence level. And the reason why is when you raise the confidence level, so if confidence level were to go up to 99, for example, 99% confidence, this Z alpha number becomes 2.576. So it becomes bigger. And when it becomes bigger, it multiplies this thing and makes the error bigger. So you actually get a larger error, hence a wider interval when you have higher confidence. A wider interval gives you greater coverage probability. It makes it more likely that you capture the mean. And so that's why that effect occurs. So of course, the other one, of course, is a consequence of that. If confidence goes down, then the interval width goes down. So that's the same idea. If you lower the confidence to, say, 90, then this number becomes 1.645. And 1.6 is smaller than 1.96, so the overall error would become smaller. The interval would be less wide. And of course, then your likelihood of capturing the mean would also go down as well. And then finally, it says if the sample size goes up, the interval width goes down. So raising the sample size is a way to reduce the margin of error without having to compromise the confidence level, right? You could reduce the error or the width in the interval by lowering the confidence, but that's a negative thing. We don't like to lower confidence. So we can accomplish the same thing by actually raising the sample size. You can see from the formula that when n becomes larger, it would end up diminishing the error, right? Because this would become larger, the overall error would become smaller. And so this should make logical sense to you because when you have a larger sample size, you have more information, and more information should mean that you will do a better job estimating the population mean. So this interval estimator should get better when you raise the sample size, and that's in fact what happens.